This section of Chapter 11 we're going to zip through fairly quickly. This deals with Raoult's law, which looks at ideal solutions versus non-ideal solutions. And the pressure, the vapor pressure of a solution, according to Raoult's law, is equal to the mole fraction of the solvent times the pressure, vapor pressure, of the solvent. And depending on the interactions between the solvent and the solute, they can be lower vapor pressures or higher vapor pressures than ideally expected. So what the graph on the left shows us that if we have an ideal solution, the vapor pressure of that solution is a combination of the partial pressure of substance A and substance B. You can look at it as a weighted average of the vapor pressure of the two substances. As mole fraction of one thing increases, its vapor pressure has a larger role and can increase or decrease the vapor pressure of the solution. If the vapor pressure of the solution is lower than expected, what that means is we have attraction between the solute and the solvent molecules, so probably polar solute, polar solvent, or we have an ionic solute and a polar solvent. So it's going to look like the far right-hand graph. If our vapor pressure is higher than expected, then what we have is really no interactions between the solute and the solvent. So we're probably looking at something that is relatively non-polar. And on top of that, we probably have something that is fairly volatile. An example of a volatile solute in its solution would be dissolving alcohol in water. An alcohol and water solution is going to evaporate more quickly than a plain container of water because the vapor pressure of the solute, alcohol, is higher than the vapor pressure of the solvent, water. And so as the alcohol evaporates, it's actually going to drag water molecules along with it, thus increasing the vapor pressure of the whole solution. Freezing point depression and boiling point elevation of substances, when we compare them to the freezing point and the boiling point of solutions containing those substances, are different. And the change is due to the number of particles in solution, not necessarily what your solute is. So the equation that we look at for freezing point depression, boiling point elevation, deals with the change in temperature between the boiling point or the freezing point of the solvent and the molality, so this is the small m for molality, of your solution. Kb is the boiling point elevation, Kf is the freezing point depression constants, and they depend on the solvent that you are working with. Here's a chart that gives you a variety of solvents, common solvents that we use in chemistry, and the normal boiling point and freezing point of the solvents, and then the constant, the freezing point depression constant, which would be Kf, boiling point elevation constant, which would be Kb, of those solvents. These can be experimentally determined. When we're looking at freezing point depressions and boiling point elevations, if we look at ionic compounds, what we need to remember is that when ionic compounds dissolve in water, they break apart into their ions. Therefore, 1 mole of a compound, of an ionic compound, is not equal to 1 mole of particles. For example, if I have sodium chloride and I dissolve sodium chloride in water, 1 mole of it, how many moles of solute particles would I end up getting? Well, I get 1 mole of sodium ions, I get 1 mole of chloride ions, so I end up with 2 moles of ions. And in the freezing point depression, boiling point elevation equations, the m for molality is moles of particles. And that's a really important thing to think about. We're not really going to take a look at the Van 't Hoff factor. That is essentially what Van 't Hoff factor is looking at, is moles of particles in solution divided by the moles of solute that are actually dissolved. With freezing point depression and boiling point elevation, especially for ionic compounds being determined not by the moles of the solute but by moles of particles, they fall into the category of something called colligative properties. Colligative properties are properties of solutions that are determined by the number of particles rather than the type of particles present in the solution. And this takes a look at Van 't Hoff factor. We're really not going to talk about it. This is taking a look at osmotic pressure. Osmotic pressure is important in any organism that is living because that's how oxygen gets into our cells and carbon dioxide leaves our cells and allowing us to survive. So if we take a look at what's going on here, as we change the concentration of the solute, we change the amount of pressure, the vapor pressure, above that solution. And what osmotic pressure tries to do is it tries to reach an equilibrium. So one way of looking at osmotic pressure is it's the amount of pressure that I need to apply to stop osmosis, or the movement of particles through a membrane. Because again, as those particles flow through the membrane, they're going to change the vapor pressure above the solvent and solution portions, especially the solution portion. So if I apply a certain amount of pressure, I can prevent that flow of particles because I'll prevent the change in vapor pressure. Here's another way of looking at osmotic pressure. So I have a solution inside my flask. I have the solvent outside the flask. If the solute particles are too large to move through the membrane, what's going to move is the solvent, and the solvent will move so as to try and equilibrate the vapor pressure outside versus inside. So we have vapor pressure here, we have vapor pressure here, and what will happen is the solvent will move to try and equalize those two vapor pressures. The difference in the column heights is equal to the osmotic pressure in terms of millimeters of mercury. That pretty much wraps up Chapter 11. What we are mostly focusing on is the definition of solutions, freezing point depression, boiling point elevation, and how solutions are different from plain solvents.